So problem 3, is that vector field conservative?
Yes.
Yes.
It's not that difficult of a question, right? You got a 50-50 shot of getting it correct. What is the more difficult question is when I ask you, as I'm about to tell me why you believe it's conservative. Yeah.
When you take the cross product, you get back for the x component, x minus x, and then for y, y minus y, and then z minus z.
So it sounds like you're computing the curl then, is that right? So if we go ahead and take the curl of this vector field f, at least one of us says that we get 0. Can anybody confirm that we get the 0 vector when we take the curl? Excellent. Well, kind of excellent. It's subtle. Has to do with the logic that's going on. Look at what, I think I wrote a very nice summary of what we just proved in the previous problem. That is, if we're handed a conservative vector field, then its curl is equal to 0. What does this statement not say? Notice, the arrow that I've drawn only goes one way. Right? This is a one-way implication. It's not necessarily the case, at least from what we've seen so far, that if the curl of a vector field is equal to 0, then we can necessarily conclude that that vector field was conservative. Right? The question is, do we have this arrow or not? Tragically, the answer is no. What's not so tragic is the fact that we only have to alter our hypotheses a tiny little bit in order to recover the statement. So it's not true in general that if you have an arbitrary vector field and you compute its curl and you find that that's equal to 0, then that vector field must have been conservative. That is not true. There are examples of vector fields who have curl equal to 0, but for who are not conservative. But it's not as bad as I'm making this. There's a light. We only have to change things a little bit. So here is it's not a total converse to what we have, it's a partial converse, but it's still pretty darn good. Here's the statement. So let F be a vector field I'll underline certain bits of this in a second. Define on all these component functions. Continuous partial view. Then curl of f equals 0 implies f equals 0. So which were the two not all that painful assumptions that we had to make in order to get the converse to this theorem? There were two pieces of information we needed to add that we didn't previously have. What's the first piece? Defined on all of R3. What does that mean for our purposes if we never divide by 0? Okay. What's the second piece? Continuous partial derivatives of the component function of this vector field. Not bad, right?
This fails.
What's that?
This fails.
This fails?
This problem fails the second
No, I don't think so. Because we've got, so for this problem, we've got everything nice and polynomial, in fact. We're not going to be dividing by anything. Everything will stay in the numerator. We can talk about that in depth in a second. But just so you can see, right, these extra assumptions that we had to add aren't really that bad. We need it to be defined on all of R3. That means we're never dividing by 0 anywhere. So we don't have this sort of a behavior for one of the component functions, I don't know, x squared over x minus 1. This is not defined. If you had an x component that looked like this, such a vector field would not be defined on all of R3 because it's undefined where x is equal to 1. Okay. So we don't want this sort of behavior. And the component functions need to have continuous partial derivatives. It's also not all that restrictive of an assumption to make. Okay. So in fact, we're good. So let's take a look now at the vector field that we've been given in problem 3. The question is this thing defined on all of R3? If you're skeptical, I'd challenge you to come up with a number, a point x, y, z, at which this thing is not defined. It's a trick question because no such point exists. This thing is in fact defined on all. And the component functions have continuous partial derivatives. Well, just to convince you, let's look at the first component function. Let's call it P. That is the x component function, which looks like yz. Well, take partial derivatives till you're blue in the face, right? If we take with respect to x, we get 0. If we take with respect to y, we get z. If we take with respect to z, we get y. And those are all continuous. They're all lines, in fact. Nothing more continuous than a line. Okay? And you can go through the same sort of check for this component function and this component function. So indeed, this vector field is one of the ones that satisfies the hypotheses of this theorem. Therefore, it's perfectly valid to use the test, is the curl of this thing equal to 0? If it is, then we're dealing with a conservative vector. Okay. If we had had something like f equals x over x squared plus y squared, y over x squared plus y squared, z, can we use this test? Why not? Why can't we use this test?
It's undefined when x squared is equal to 0.
This thing in particular is undefined at the origin, so this vector field is not defined on all of R3. Okay? So if you come across a vector field that looks like this, where you're doing some funky dividing by 0, this theorem does not apply. So it could be the case that you go through and you compute that you get the curl of this thing is equal to 0, but that does not imply that it's conservative, because it didn't meet the hypotheses of this theorem.